Okay, shall we continue? Good. This was the list of topics that I wanted to cover. You see that we did rather well. We covered the first few. And nothing is perfect. Even imitation can be imperfect. Now, okay. That was the question, the ingredients. We had looked at the mechanism, which was the Bolton model, how this is modified by complex networks, and how is this modified by this question of aging. Now what I want to do is to elaborate a little bit more, putting another possible ingredients and see which are the consequences. So putting this mechanism in a little bit more of detail or other circumstances and see what happens. And the first thing that I would like to introduce is this concept of imperfect imitation, or if you want, noise. Now, and this goes under the name of the noisy Bolton model. The noisy Bolton model has been discovered and rediscovered in many fields and papers without cross-referencing, so without everyone knowing that this thing already existed for some time. And here you have a number of references, as you see, even in genetics, that was pure statistical physics, percolations, sulfur reaction. And what I will follow is this presentation, which I particularly like, by an economist, Alan Kirman, in the Quarterly Journal of Economics. The model is the same. I mean, the context or the narrative might be different, but the model is exactly the same. And the paper is called Ants, Rationality and Recruitment. And even he has movies with ants that they can follow two paths, one or the other, to go from here to a place where there is some food. And he makes an analogy of that with the stock market, in which going this path is selling, going this other path is buying, and makes some sort of interesting analogy. So let me try to make this presentation of the noisy Bolton model in terms of this economic context. You have brokers in the stock market, and some of them are optimistic about what it is going to happen. And so if they are optimistic, what they want is to buy. And the others are pessimistic about what it is going to happen, and they want to sell. So you have two states, as in the Bolton model. One, it is buying, the other is selling. It is optimistic, it is pessimistic, whatever you want. And of course, each of these agents in the stock market interacts with other agents, being ki, the degree, so the number of people with which this broker interacts. Now, the question are the transition rates. How do you go from a state of optimism to a state of pessimism, or from buying to selling? And the transition rates has two terms. This term here is the herding behavior, which is the Bolton model. This rate is just H is the strength of this herding mechanism. It is proportional to the number of neighbors in the opposite state. So it's Bolton model. You are going to imitate randomly one of your neighbors which are in the opposite state. So this is the herding mechanism. But there is this other term here, which is called idiosyncratic in the economics literature, that for physicists is noise, which means, well, randomly I change from plus to minus. And if you want, in social science literature, it could be even called free will. What do I mean by free will? Is the ability of doing something independently of what the others do. I do it because I want to do it, because I have this ability to do it independently of what the others do. This in physics is noise, change from one state to the other, independently of what the others do. Okay. Then when we introduce noise in the Bolton model, which is the main mathematical effect? The main mathematical effect is that there are no absorbing states. Because even if everyone is in the same state, due to this noisy effect, I mean, there is a way to escape from the absorbing state. Okay, then, okay, here, now it is blue and red. I mean, there are two states, okay? Now, this is the number n of people in this, and this is a fully connected network again. We are in the n, this is the number of agents in green, and the number of agents in red. Now, the probability, okay, the probability for one of these green to become red is proportional to the number of red, and then you have these two factors, the one which is the herding behavior and the one which is just noise, if you want. And then it happens that you have a competition of this herding behavior and this noisy term, and in fact you have two regimes. The one which is dominated by noise, in which, I mean, the mean number of, or the number of agents in a given state just fluctuates randomly around half of the population, or the one which is dominated by herding. If it is dominated by herding, you go close to one of the absorbing states, but because of noise, you change to the other, okay? And it is this going from the optimistic to the pessimistic consensus due to noise, you do not remain there, which was the analogy by Kierman in this selling and buying changes in the stock market. Now, if you do a very simple description of this, which you just look at the probability distribution, okay, for the number of agents, what you see is that you have these two regimes. This one is a probability distribution which is picked around the two values, okay? And then you have the other state, which is the one dominated by noise, in which the maximum is around half of the population. And you have a transition that goes from here to here. If you characterize this transition by looking at the maximum of this probability distribution, so that's the probability distribution for the number of agents in one in a given state, what you see is that you have, when you are above this transition point, this maximum is at 0. When you are below, you have these two maximum. Now, this is a finite size noise-induced transition. Why finite size? Because the critical point goes to 0, as n goes to infinity. As the system size goes to infinity, this disappears. And it is noise-induced because the control parameter is the noise intensity, or if you want, the ratio of noise to herding. Now, just a few comments because this allows me to introduce another method in the analysis of this noisy Bolton model in networks. What I'm showing you here in terms of simulations is this critical value from this transition from herding dominated to noise dominated as a function of the the normalized variance of the degree distribution of the network, okay? This is the result for the random network, which is well given by the pair approximation that I've told you before, and this is the result for the Barabasi-Albert network. This is for the dichotomous network. A dichotomous network is that you have a degree distribution with two different peaks, although the mean degree is the same. And this line here is this nil approximation for uncorrelated networks, and this is just an excuse to introduce this approximation. what is this anneal approximation for uncorrelated networks? Okay, what you do is you replace the actual network by a fully connected network in which there is a weight to the different links. And the weight to the link that connects node I with J, so that would be the adjacency matrix, is just that the probability that node I with degree I is connected to node J with degree Kj. So in a sense, you replace the actual network by effective fully connected network in which the weights of the link are associated with this probability. In this approximation, you can calculate exactly this critical one, and this is what you see here. Now, this is the very global view of the network. If what happens with the local ordering, this idea of growth of domains. What I'm showing you here is for a random network, this number or average number of active links as a function of time for different noise levels. This is the Bolton model, where there is no noise, so that eventually you approach to the absorbing state, and this is increasing values of noise. What happens, as I said before, is that the noise destroys the absorbing state, and what we reach here is an asymptotic state which is partially ordered. When the noise is low, what you see is that you are close to this is the Herding-dominated regime. You are close to the absorbing state, but noise is kicking you out of this absorbing state. While in the noise-dominated regime, what you have is that this is around a plateau with some random excursions out of the thing. And if you look at this transition here, okay, I'm plotting this stationary value, which are those values here, as a function of the noise intensity. And this is the mean field pair approximation that, as you see, it is good for A equals 0, but there is a singularity at A equals 0. So it only works well for relatively large values of noise. And these other lines are this approximation of anneal approximation I've shown you before that goes well here. So, well, those are different approximations, but the transition is only reflected as a crossover regime in the local ordering, which is this region here. So this type of transition, noise-induced finite size transition, at the level of local ordering, it is just a transition regime. And this imperfect imitation, you see that it is only sensitive to the network. So those squares, circles, and triangles become different when the network is only sensitive to the network topology when it is not dominant. So when the noise is rather small. Now, so this is to mention what is this idea of noisy Bolton model, and I'll come later back to that. But let's see. What happens if now I started with the Bolton model as a single mechanism imitation, and now I am adding two things, as someone was asking there. First, I have added noise, and now I am going to add aging. And you will see that that has important consequences. In the noisy Bolton model, what I have here is this noise-induced finite size discontinuous transition. In which sense discontinuous? This is this probability distribution that I was showing before. And so what happens is that I go from a distribution peaked around the two extremes, and at a given transition point, the distribution becomes flat, and then the maximum here starts to grow. So this is discontinuous. Now, if I put aging, and those are the result of the simulation, what you see is that these two peaks, as I increase noise, become closer, closer, closer together, and they collide here. So the transition becomes continuous. But it is not only that it becomes continuous, it is that it becomes a well-defined transition to the eyes of the gods of statistical physics. So that means that it is not a finite size transition, but it is a transition that occurs in the thermodynamic limit. What I'm plotting here is this, one can do theory here, and this is this mean magnetization in absolute value as a function of the noise intensity for different system sizes. What you see is that the transition becomes continuous, and it is well-defined in the thermodynamic limit. This is just a finite size scaling of the transition. And it turns out that this phase transition belongs to the Ising universality class. If you do it in an Erdos-ready network, which is of effective dimensionality, because and the critical dimensionality is 4, you obtain the exponents of the mean field universality class. If you do this thing in 2 or 3 regular lattice, you obtain the Ising exponents in these dimensions. So what I'm telling you is that before the break I was telling you, wait, aging is essential. I mean, it leads to ordering when there was no ordering in the Bolton model. What I'm telling you now is that if you put aging in the noisy Bolton model, what was a finite size noise-induced transition becomes a well-defined phase transitions in the concept of statistical physics, which belongs to the Ising universality class. Can we understand what is the origin of this transition? A phase transition in statistical physics is associated with some symmetry breaking. What is the symmetry breaking that occurs here? The symmetry breaking is asymmetric aging. What I'm plotting here is the mean, okay, you have 2 populations in your system, one which is state plus and the other which is state minus. And you can calculate the mean age of each of these populations. Each agent has an internal clock, which is its age, how long they have remained in the same state. Now, this is the mean internal time of one population in red and of the other population in blue, and this is the difference between the two. What you see is that what happens at the critical point is that there is a spontaneous symmetry breaking. One of the 2 populations becomes older than the other, okay? And it is this symmetry breaking in the internal age of the population that produces this phase transition, okay? So again, something that one can learn from a simple model, statistical physics-like. We've already learned that aging is important, but it is beyond that. If we add something, which is this imperfect imitation, it is symmetry breaking in the age of the population that can induce this transition. Next concept that I will use the Bolton model to, as I said at the beginning, I'm using the Bolton model to introduce a number of concepts and approximations in this field. And now I want to talk about coevolution. That was the question, okay? We've talked about mechanisms, now even imperfect imitation. We had talked about complex networks, but I now want to talk to another aspect of the network. And the aspect of the network is that the links are not persistent, that ties are not persistent. I can have relation with someone, and after a given time, I break this relation, Okay? Now, this is about dynamics of networks. And when people talk about dynamics of networks, they normally mean two different things. One is the dynamics of network formation, so how a network grows, okay, which is the structure of the network created. And there is another aspect, which are the dynamics on the network. This is what I've been talking about. The network is given, and the nodes have some state, and I have some dynamics on the network. Those are two different things. In fact, from a sociological point of view, this corresponds to 2 points of view in society. The right-wing view, in which the structure, the network, is created by individual choices or actions. This is the dynamic of network formation. This is the left-wing view, in which the action of individuals are constrained by the social network. I mean, you are born when you are born, where you are born, and you are stuck there, and those are your possibilities are given by this initial state. Of course, there is a third possibility, which is the coevolution of the agents and the network, which means that circumstances make men as much as men make circumstances. It is true that you are in a network that constrains your possibilities, but it is also true that you can modify this network. So this is not that new. Michael Macy is a professor of sociology in Cornell University, and he already has this quote in the American Journal of Sociology, in which he proposes a new research agenda in which the structure of the network is no longer given, but a variable. And the idea is to explore how a social structure might evolve in tandem with the collective action it makes possible. The key idea is that the structure of the network is no longer a given, but a variable. It's something evolving in time. So the final goal is the understanding dynamical processes of group formation and social differentiation, emergence of social dynamical networks with social structure, community structure, and so on. Now, let's try to put this very general idea in the context of the Bolton model. The idea of the coevolution is the dynamics on the network coupled with the dynamics of the network. It is not only to imitate neighbors, but it is also about choosing neighbors. Okay? So let me create a cartoon on that. This is social imitation by imitate others. This is described by the Bolton model. And I remind you, is this idea, a node, red, a random one, blue, and I imitate this random neighbor, and I also become blue. But then it is also about breaking and establishing new ties, okay? So it is about rewiring. I don't want to talk anymore with Pablo, and I will talk only now with Mauro, okay? So what is the idea here? The idea is I choose this node, which is red, one of the neighbors, which is blue, and the social imitation was this thing I had before, but I can do something else. And I said, I'm fed up of this neighbor which is of a different color with me. I break this link and I establish a new link with someone which is in my same state. Okay? This is the idea of a coevolving model, non-persisting ties. Okay? Now, typically, what happens is that this process of imitation plus the idea of choosing networks leads to a network fragmentation transition, which is one of the ways to understand social group formation. When imitation is much stronger than this rewiring process, I reach consensus in one of the states. But when the rewiring process is more important than the imitation process, the network breaks into two groups, each of them in a different state. So we have a fragmentation due to the competition of two time scales. Which are these two time scales? One is the evolution of the network, the rewiring, the dynamics of the links. And the other time scale is the time scale of evolution on the network, the time scale of evolution of the changes of states in the node. This ratio of time scales is measured by a parameter that we call plasticity of the network. And what happens is that for a critical value of the plasticity, the network breaks into two, and we have a fragmentation transition. So let's put that into a little bit more of detail. Again, nodes that take states -1 or +1, and then this is the dynamics. I choose this node, which is red, a neighbor one, which is blue, and then I can do two things. With probability P, which is the plasticity, what I do is I rewire. I'm fed up of this guy, I cut this link and establish a new one. This is with this probability. With the complementary probability, which I do is the normal Bolton model. I just imitate and copy. Okay? And repeat that ad infinitum. So the crucial idea is that the agents select interacting partner according to their state. Okay. And P, this probability gives a ratio of the time scale of evolution of the state of nodes and the state of the network. So this is the idea of coevolution. It's a new parameter that I'm introducing as the ratio of two time scales. This can be done, or this can be put into mathematical terms in the pair approximation that I described before. This is the equation that we had for the pair approximation when the network was fixed. And you see that the change it seems not very deep. It appears this plasticity here, okay? So you see it's a small change. But this small change has an important consequence. This is in the thermodynamic limit. You're looking for the stationary state of this equation. And what you see is the evolution of this thing as a function of time. For large plasticity, it goes to 0. For small plasticity, it goes to a finite value. What we are finding here is an active frozen transition at a critical value. When the plasticity is smaller than this critical value that we can calculate, mu is the mean degree of the network, we have a finite value of this average number of active links. That means that we are in an active phase. We are in an active phase of coexistence of the two opinions because the number of active links is not 0. And beyond this critical value, we have a frozen phase in which we have reached some sort of consensus. Okay? Now, this is in the, so again, in the active phase, what happens is that links are continuously being rewired and nodes continue flipping state. In the frozen phase, there is a fixed network where connected networks have the same state. Now, this is a description in the thermodynamic limit, the pair approximation. The manifestation of this active frozen transition in a finite system is this fragmentation transition. If you look at the size of the largest network component, below the critical plasticity, you have a single component of the network in a single state. Beyond that, this size of the largest network component goes to 1/2, and you have these two blobs. So the active phase of the thermodynamic limit becomes a connected network reaching consensus. the frozen phase corresponds to a fragmented network with two blobs in different states. I will not go into that, but you can do your statistical physics of that, and this is a well-defined phase transition in terms of active links, becomes well-defined in the thermodynamic limit. You have critical slowing down, you have exponents, you have everything you want from the point of view of statistical physics. What is the physics or the concept of that? When the plasticity is low, you have a slow rewiring. And slow rewiring keeps the network connected, and if the network is kept connected, the system fully ordered and freezes in a single component. But when you have fast rewiring, this fast rewiring leads to a fragmentation of the network into two components before the whole network can reach the consensus state. So, again, by this simple statistical physics model, we are able to identify an important parameter of the dynamics. And this important parameter is the ratio of time scales of evolution of the network and time scale of evolution of the nodes. Okay? So this is the summary for this absorbing transition in a coevolving networks. Coevolution in systems with two absorbing states induces a fragmentation transition. And the fragmentation is explained as a competition between the rates at which network and the state of the network of the nodes evolve. Let me continue this thing of putting together different mechanisms and different pieces. Now, I have this coevolution, and well, what happened with the imperfect imitation? Let's have a look at that. This is the coevolving Bolton model. I have session imitation and I have rewiring. But now, I have noise, which means that some agents randomly change state with a given probability independently of what the others do. Okay? Free will. So now we have two parameters. One is the plasticity of the network, and the other one is the noise intensity, the ratio at which agents changes state independently of what anyone else is doing. What happens? Noise, once again, destroys the fragmentation transition. Why? Because there are no longer absorbing states. But in spite of that, one can look at three regimes which are separated by finite size noise-induced transitions. What I'm plotting here is the noise intensity, the rewiring probability, okay? And those are transition lines that depends on system size. In fact, these transitions disappear in the thermodynamic limit. Let me go first with this regime here. This regime here is the regime of low noise and low plasticity, low rewiring. And for zero rewiring, we had this transition here, which was the finite size noise-induced transition of the noisy Bolton model. What we find here is what we call bimodal magnetization. The network doesn't break. The size of the largest component is always 1, but we have this, what happens? I cannot see the movie here. I'm sorry, neither here, okay. Well, I wanted to show you some movies, but somehow the links are not there. Let me explain you with words. What happens here is the size of the largest network component is always 1, so the network doesn't break. But you have a single network which at a given point is everything is blue, then it shifts to everything is red, stays there, shifts again to everything blue, so you have this network connected which is changing from one consensus state to the other consensus state. Now, when you go here, which is a state in which both noise and the rewiring is large, crossing these transition lines, again, the network does not fragmentate, but you see that the average magnetization is around 1/2. So what you have is a single network in which randomly the nodes are blue and red and they are changing. You have this coexistence. Fully mixed. It is dynamic. And the last state is this one for large rewiring and low noise, where you have this, that is what we call dynamic fragmentation. If you look at the size of the largest domain, you see that it is around 1/2, but it goes to 1/2. What you see here is two domains, one which is blue and the one which is red, and these domains are connected by a few links. But it never fragmentates because the links are rewired again due to noise. So you have sort of dynamic fragmentation. Okay. So what you see, what I'm trying to, what we are learning here is that, again, putting two of these mechanisms, one is coevolution and the other is noisy Bolton model, we destroy in some way this fragmentation transition, but we have some remainings of them with these transition lines. Okay. Multiplex Bolton model. The idea here is, again, to explore a little bit more the question of the network. First thing I did was to explore the tie heterogeneity, the topology of a fixed network. We talk about coevolution, but then we need to talk about context and the idea of multi-layer or multiplex or interconnected networks. What is this idea? The idea is about social context. The idea, we have a mechanism which is imitation, but normally we interact at least at two levels. One is our network of interaction, say, at work, and our network of interaction of family and friends. And this network of interactions might be different, okay? And this is the idea of multiplexing, which is the social context. How does it go in the Bolton model? The idea in the Bolton model is that a given agent is in these two layers, and then one interacts with the Bolton model in one layer. I'm copying here, okay? So I become blue, and then this change of state in one layer has to be also imposed in the other layer. By doing that, remember at the very beginning today I said the Bolton model has no parameters. Now I am slowly introducing parameters because I am introducing new mechanisms. Here I am introducing two parameters. One is the degree of multiplexing, and the other is the edge overlap. Which are these two parameters? The degree of multiplexing is the number of nodes that are connected in the two layers. That means if this node here and this node here are the same, they are connected. They have this interlayer link, okay? But there are other nodes, like for instance, this one, which is in this layer, but it is not in this layer. Then this normalized number of interlayer links is what we call degree of multiplexing. And the other thing is the edge overlap. The edge overlap is how many of the links in one layer coincide with the link in the other layer. Or if you want, how similar or different is the network in one layer or to the other layer. I will not go into the details. I'll just give you the results. When I do this Bolton model in these multi-layer networks, what happens, the main result is the same. If I have random networks, I do not reach consensus in the thermodynamic limit. There is no ordering, so the mechanism of imitation in a multi-layer network does not lead to consensus. This overlap is not relevant parameter. Look at what we are doing here is we are introducing mechanism parameters, and in the spirit of universality, what we are looking is which of them are relevant. I told you that the topology was not a relevant thing. I'm telling you now that this overlap is not relevant. And the other important thing is that in this sense here, topology becomes important. You cannot reduce these several layers to a single layer dynamics. Now, having said that, let me show you how multiplexing interacts with coevolution. I insist, in this second part, I'm trying to put together different things and see how they interact. So this Coevolving Bolton model, which was social imitation plus rewiring, that was leading to fragmentation transition. And now I do this thing, but into multiplexing context, in which nodes represents agents and layers represent context. Now, what are the parameters here? We have two layers. Each of them is coevolving. So we have two plasticity parameters, or two rewiring probabilities. This is the one of layer 1 and the one of layer 2. And then we have the degree of multiplexing, which is the interlevel connectivity. How many of the nodes in layer 1 coincide with nodes in layer 2? We will just use random regular networks with some given degree. This is not important here. So what is the dynamics? The dynamics is, at random, I pick one of these two levels. In this level, I use the Coevolving Bolton model. The Coevolving Bolton model says that with some probability, I do rewiring, and with some other complementary probability, I just imitate. And then, after I have done that, I synchronize the state of the node across levels. So if these two nodes are the same, then they have to have the same state. Okay? So this is multiplexing and convolution. Which are the consequences of that? Then let's start by the simple case. The simple case is in which the two layers have the same plasticity. So the two layers have the same ratio, of time scales of evolution. And this is the active phase, and this is the frozen phase. In a monoplex means a single layer, I had this transition from active to frozen. What I see, and this corresponds with zero multiplexing, when I have fully multiplexing, all nodes are present in each layer, this is the transition I have. So what I find, and this is in the thermodynamic limit, this is finite size, this is the fraction of the largest component. So what I see is that essentially this absorbing transition or fragmentation transition, they persist, they are still there, but they are shifted with connectivity. They are shifted from here to there or from here to there. So in conceptual terms, what you see is that multiplexing prevents fragmentation. Why? Because, okay, for this plasticity in a single layer, the network has already fragmented, but if I increase the multiplexing, this transition is delayed. So the idea of different context prevents fragmentation. Now, let's go to the other extreme. The other extreme is in which I have two layers which have very different plasticities. And I go first to the extreme case in which in one layer I don't have imitation, I only have rewiring. And in the other layer, what I have is no rewiring, only imitation. If there is no multiplexing, so nodes are not connected across layers, well, this is fully dynamic, it fragments. There's no dynamics, it does not fragment. This is what happens when I have an intermediate multiplexing. I can show you, I hope this, I don't know what happens today with the, well, I didn't look at the links. Anyhow, what you see here is that there is a fragmentation, but what I call a shattered fragmentation, because this layer fragments into two, but there is additionally a very large number of isolated nodes, which are the ones which are connected to the other layer. So what happens is that we have a new form of fragmentation that we call shattered fragmentation. Here, this was for extreme asymmetry in the plasticities. What I'm showing you here is, this is a very large plasticity, but it is not only rewiring. This is low plasticity, but there is some rewiring. And here you have what is the final state of the two layers for different values of the multiplexity. Here, this layer is isolated from this one. There are no interlayer links. And in the other extreme, each node is the same in two layers. There is fully multiplexing. And let's see what happens, see if this works at least. Okay. They were working on the plane when I was preparing my talk. But it is just a movie, you see what happens here. So what is the result? Well, you see that somewhere between this and this, around 0.7, there is a critical degree of the multiplexing that depends on the two plasticity that prevents fragmentation of the dynamical layer. So if this is Q.7, here there is no fragmentation of the dynamic layer. And this is a critical value of multiplexing that depends on these two plasticities. And below this critical value, there is fragmentation of this layer, but it is a shattered fragmentation. Shattered in the sense that the layer fragments into two main groups, but there is like an explosion of isolated nodes. Okay? So, summary. First thing, multiplexing can prevent fragmentation. There is a critical degree of multiplexing for a fragmentation of the level with larger rewiring, right? And the fragmentation transition is anomalous in the sense that we call it a shattered fragmentation. Okay. I repeat my message. I started with a very simple model and a very simple question, and there were no parameters, okay? Now I've introduced different things, and I've seen how these things might combine and how these give rise to different parameters and different effects that one can look at. And this is what we learn from these simple models. Now, the question is, we've learned something. This is good enough. This is what we do in theoretical statistical physics. learning about models and mechanisms and transitions. But of course, one would like to see if this has anything to do with any form of reality, if there is any data validation of these things. And I'll give you very briefly 2 examples that take into account part of these different mechanisms. So can we go beyond understanding mechanisms? What about data? And I'll give you 2 examples. One is how by these simple models we can describe the community structure of online games. And here, what we have to combine is imitation, coevolution, and multilayering. Those are the 3 things that we have to introduce. And second, this is, well, now a little bit old paper, but I think it is still good for pedagogical reasons, which is, it has to do with the presidential US elections. And here the mechanism that I need to introduce is imitation, imperfect imitation, and the concept of mobility. So let me go with the first one very briefly. You know there are many online games. Many of you may be playing some of them. This is one, okay? And this is the Pardos game. It is popular in Austria. And, well, look at it if you want. The important thing is that there are that people there interact in different ways. They establish friendship. I'm a friend of that. Then we exchange messages, we communicate, and then we trade. We exchange money, commodities, or whatever. So it is one of these games in which you do several things. Now, what happens is that the proper way to study the communities that are created in this online game is to look at different layers, because there is the layer of the network of who is friend of whom, the layer of who communicates with whom, and the layer of whom you trade with. And those are 3 different layers, and you can create these networks by looking at the data for a given year. And it turns out that, of course, these layers are evolving in time. And if they are evolving in time, you can determine the plasticity of these layers, so how they are rewired. And it turns out that here is this plasticity parameter. This is the size, doesn't matter. Well, you see that the friendship layer is much slower in its evolution than the trade and the communication layer. So we have layers in which the network, evolves much slower than the others. And the question is, if with these ideas of coevolution, we can understand the structures of the communities that appear in these layers. Okay. First thing one can do is to compare the topology of, well, we have 3 layers, but let's compare what happens with one which is slow and the one which is fast. The slow one is friendship, one fast one is communication, and another one is trade. What you do is you do several empirical or several measures from that analysis of comparing the network in each of these 2 layers. Either Jaccard coefficients of edge sets, degree correlation, degree rank correlation, and you compare data with model, and you see that you have a rather good agreement. So it looks like that the different structure of the networks that you obtain can be explained in terms of this imitation process plus coevolution of the network. Beyond that, the model I showed you was for 2 layers. You can do it in 3 layers. And then you look at the community size distribution. Okay. What I'm showing you here is the friendship layer, the trade layer, and the communication layer. Data in blue, model in red, and the different symbols correspond to 4 different standard ways of detecting communities in a network. And what you see is that for the friendship layer, which is the one of a small plasticity, you have, well, something like a flat tail distribution. You have a small number of very large communities. While in the other 2 layers, which are of large plasticity, you have a distribution which is rather well picked. So you have a large number of small communities centered around communities of 50. This is just an example that with this type of modeling, in which here I insist what we've put together is imitation, is multilayering, and coevolution, you can give an explanation of the community size distributions in one online game. And to finish, let's go with electoral processes. Okay, this is analysis of data from the presidential elections 1980-2012. This study was done 2 years later, this presidential election, and I think no one had the courage of looking at the last presidential election. We just didn't like the result and forgot about it. But at least so it's not a very updated result, but I think it is good for several pedagogical reasons, and that you can learn about that. What I'm showing here is in the different counties, the evolution of the Democratic shares in different years, and the one of the Republican shares. Beware of the colors. Here, red and blue is this scale. There's nothing to see with the color of the party. And, well, this is a spatiotemporal distributed data, okay? And this is the data that you would like to understand. Now, the first thing that you need to do is to find some statistical regularities in this data, okay? And, well, the one thing that you can do is to look at the global percentage of voters for each party around here, and for the turnout, so how many people went to vote. The turnout is in black, and red here corresponds to Republican, and blue to Democrat, which are their colors. This year here was, what was the name of? This was 1 year that, in fact, there were 3 main parties competing. One good thing about studying this thing in the US is that it is binary. I mean, in Europe, it's a little bit more complicated. What was the name of this? Well, I don't remember. Okay, now, what do we do with that? Look for statistical regularities. And the first thing that you can do, this is the turnout, and this is the vote fraction for the 2 parties. You just look at the distribution for different years, but you look at the distribution for different years subtracting the mean. So you put the distribution with the same mean value. And what do you see? This is statistical regularity. The distribution, if you subtract the mean, is the same in all the elections, okay? That what means is that what is important is who wins. But if you forget about who wins and you put the mean, the statistical path around that is always the same, okay? And in fact, this has been used to show that there are elections which are fake if this doesn't happen. For instance, the last Russian elections, some colleagues look at the results, wrote some papers, and they got calls from the Russian embassy because it was clear that there was something wrong on those results. Now, this is for these probability densities, but Philippe Bouchot in France, what he did look at different, those are different European countries, and look for something else. Looked for a spatial correlation. So the correlation of this was not the vote, but the turnout in different countries, how the turnout in one location is correlated with the turnout in a correlation some kilometers away. And what he finds is that these decays, which are similar to a logarithmic decay, okay? Now, if you do that with the US, and this is not for turnout, but for vote, for real vote, what you see is that, again, you have these things which are looking like logarithmic decay, okay? And this is what you would like to explain. Now, let me make clear which is the aim. You have something like looks like a logarithmic decay. You are a physicist and you say, aha, logarithmic decay means diffusion. So if you only want to, I would say, reproduce this data or summarize what type of process is there, you can write a diffusion equation. A diffusion equation in a field theory. And this is what Bouchol et al. Did. And yes, well, this is a model to reproduce this data. What we wanted to do was something different. Is, can we construct an individual-based model which going from the micro processes between individuals to the macro level, we reproduce these things, okay? It is not just to fit the data with a diffusive equation, but go from the individual model to that thing. And let me make clear, this is not an attempt to predict electoral results. What we are trying to do here is something which is independent of who is winning the elections, is to try to understand these fluctuations or heat bath in the electoral processes. Subtracted the main political effect, which is who wins. Okay, so we show this transparency. This is the normal spiral that is shown about interaction of data models and whatever. Now, we have data that we want to understand, and that we then have a mechanism, which I will claim is imitation theory, that interacts with that. And then we will have some input data, which are the social context. And this is different from trying to infer a model that reproduces this data. This is what statisticians do, and in many cases, artificial intelligence and these new approaches are trying to do, which is to infer a model that reproduces this data if nothing in the boundary conditions are changed. We are trying to understand mechanisms that do that. Okay. So the ingredients of the social influence model: interaction mechanism. My interaction mechanism is imitation as a basic manifestation of social influence, and this is where the theory and modeling are. But then there is a social context, which is the set of all possible interactions, and we model that as a network of interaction from census data. And this is the input data that we take. So let me start with the input data. The input data, this is the network of counties, of electoral counties in the US, because they are connected if they are adjacent. And this is, roughly speaking, an hexagonal regular network with this number of counties. And we've looked at that in other countries, in particular in Spain, and these counties or the electoral places in many cases form this sort of quasi-regular, quasi-hexagonal regular network. But the other input parameter that comes from the census, well, in the census you declare where you live and where you work, so that you can also construct the mobility network. And this is from the 2001 census data. This mobility network is a direct weighted network, And in terms of population, which is rather heterogeneous, well, you see that the population with the county with the largest population is in Los Angeles, the one with the smaller population is in Loving, Texas, and here I didn't, all these also the commuters from this commuter network. The largest number of commuters are from Kings, New York to New York, and well, so this is input data. Those are parameters, okay? Which is the model? The model is a metapopulation Bolton model, which is very simple. We have a number of agents that interact in the Bolton-like interaction, random copy. There are n sites, which are counties, and each agent is considered in two sites, where the agent lives and where the agent works, okay? And there is a probability to interact at home and a probability to interact at work. But the interaction is just copying. There is a parameter which turns out to be relevant, which is this interaction probability at home or at work. So, repeat, an agent interacts with probability alpha with anyone that lives where she lives, and interacts with the probability 1 minus alpha with anyone that works where she works. So, those are the input parameters, and parameters that we know, which are the location of each county or of each city, the number of agents that live in I and work in J. And so this is the total number of agents that live in I, and this is the total number of agents that, how is that? Sum over J, yeah, this gives you the total number of agents living in I and the complementary. And which are our variables? Okay, this is what we want to look from the model. Are the number of agents living in one county and working in another one, J, holding a given opinion plus 1. And then the correlations of these densities. This is what we want to calculate. Okay, I don't think I have time to go into the details, but just let me give you the idea. Those are transition rates for a master equation that take into account this imitation process, depending on the populations, okay? So it is at a meta level, it is not individual by individual, it's by populations in different counties. And when you write that into a master equation, as I said at the very beginning today, you do a system size expansion and you go down to a Langevin equation. This is the Langevin equation that you write, and you discover two things. If you look at that into detail, you will see that this thing has the structure of a diffusion process. And this is the noise term, and the noise term scales with this 1 over this number, which was number of agents living in I and working in J. Typically, this is a rather large number, so typically this noise is very small, which is this internal noise of the process. Okay, we have these equations, so we simulate them with an initial condition, which is the Democrat share in a given year, and you just do that for several years. What do you see? Diffusion. It smooths out. Okay? So the probability, subtracting the mean for the vote for the Democrat share, you see that it is something that, as time goes on, collapses because it spreads. And if you look at the correlation, what you see is that correlations grow, while the data says that this is constant in time. So, doesn't work. This is not what we observe. So we need something else. The important thing that we need is that this distribution becomes stationary, and this is constant at different times. The extra ingredient needed is imperfect imitation. So there is some noise. I mean, there might be a few people that have an opinion independently of what their neighbors do. Some free will. So what we do is to include imperfect imitation in these transition rates, which is noise. You do the same thing, and then you have a noise term in this Langevin equation. And this is the noise that scales as 1 over the square root of n, and which is small, and that you can neglect that. So now you have this external noise, and you have introduced a new parameter. Believe me, this parameter alpha that was interacting at home or at work doesn't change anything, it just changes time scale. So the problem is left with a single parameter, d. So we have to calibrate noise, because it's the parameter of the model. And if you look at the Bolton standard deviation after 1,000 Monte Carlo steps, this standard deviation as a function of the parameter noise, this is what we had when the noise was very small. It was just a diffusion process. Didn't work. This is when we have a very large noise. This is a noise-dominated process. A noise-dominated process, you know, with 2 peaks around in each country around the 2 things. But there is an intermediate value of noise, is the calibration, in which the standard deviation of the Bolton distribution remains stationary. Remains stationary and fixed empirical value data. So we fixed 2% as the free will in the US presidential elections, which is this single parameter here. With this value for the imperfect imitation, single parameter, well, then we have to calibrate. I mean, this is always the same problem in how to relate Monte Carlo steps to real time. Well, 10 Monte Carlo steps corresponds to 40 years, 1 election period. Okay, what I'm showing you there is I take as initial condition for the Democrat share for the year 2000, and then how this thing evolves along the years. This is the data, and this is the model. You see that we have this stationary distribution when we subtract the mean, okay, that it is there along the times, and the spatial correlations, the logarithmic decay, which remains stationary for several years. This is what we wanted to do. Now, let me show you in which sense we have made a prediction or we have not made it. We have not made it. This is the results for the Democrat Party. This is data, this is the model with this initial condition. Well, it is not very good. In fact, what happens if what you do is you subtract the mean? If you subtract the mean, the 2 things are much more similar. In fact, data minus model, if you do not subtract the mean, as you see, well, this is the scale. While here, the scale is really around 0. So the idea is we forget about who has won, but we look at the fluctuations around that and the correlations in these fluctuations. And this is well fitted by this model. Okay? So what we've done is an individual-based model implementation of a microscopic mechanism leading to diffusive mesoscopic stochastic dynamics that reproduce the statistical regularities of the election data. It is data-based because there are input parameters that we know. but there is a single calibrated model, a single calibrated parameter in the model, the noise intensity. What do we explain? We explain two generic features in the background of election results: the stationarity of the dispersion of vote shares and the time-persistent logarithmic decay of spatial correlations. I didn't talk about that, but also about different length scales you get these things. But there has been no attempt to predict electoral results. This is as far as one can go. Have we proven that this is what happens? No. We've proposed a model that reproduces these statistical regularities, taking into account some mechanisms. There might be alternative explanations, possibly, but it is up to anyone else to propose an alternative explanation which is simpler than this. And then that would be a better explanation. Okay? Right, it was finishing. So to wrap up of what I've tried to do today, the title was, what can we learn from simple statistical physics models in social dynamics? Well, with simple models, we can isolate the mechanism, see consequences, understand mechanisms, understand statements which are wrong, right? And then we can start putting together some of these things. And putting together the ones that could be relevant in different contexts, we might account, or we might explain some of the data that is observed in different phenomena. I gave you two examples. One was the community structure of online games. Another one is this of the electoral processes before the last US electoral process. That's it. Thank you.
Do you have any questions?
That's okay. So you showed that if you have this parameter d, it's too small, the distribution collapses in one direction. Too big, it collapses in the other. Is it really a single value of d that
it is the value of d that better fits the results.
But I mean, just so let's forget about, let's say the only result is stationarity of the distribution. Does that actually require a particular value of d?
No, it's a range, or narrow range of values. Narrow range of values of d.
But then I guess a non-trivial thing is that when it becomes stationary, it has the right variance.
Excuse me, when it becomes stationary?
When you set the parameter to make it stationary, it also comes out with the correct variance.
Yeah.
Which is not obvious that should happen. Right?
Yeah.
Any other?
On the model that had both plasticity and multilayering, if my eyes didn't trick me, there was a final state in which, in the same layer, there were groups of elements which had the same opinion but were not connected. Right?
Same opinion but not connected? No, there is, okay, let's go to it. I'm sorry the movies I had didn't work here, but back to this here. Here? Okay, you have this group which is connected, and the other one which is the blue one, and then what you have is this explosion of isolated nodes.
Yeah, so those red nodes that are on the outside.
Those nodes have all the, or should have, I see, look here, they all have the same color because those are the ones that are connected to the bottom layer.
Yes, but they are not connected to those on the middle of the ring.
No, that's what I mean by shattered fragmentation.
Yes.
And you have two main groups, and then a large number of isolated nodes.
Is there a message to be drawn for that? I mean, without the multilayering, there was only segregation between people that had different opinions. But now, with only the addition of an additional layer, people with the same opinion are not connected.
Well, because you have here a constraint, which is this level of multiplexing. This level of multiplexing tells you that there are a number of people that have to have the same opinion in both layers. And this is the constraint. I mean, if you are the same person in the two layers, you have a given opinion. And this is the constraint. And this parameter Q, which tells you this degree of multiplexing, that in a sense is a measure of the number of interlayer links.
Okay, thank you.
Any other? Okay, let's thank Maxi again.